Hi, we're Robocol, a multidisciplinary team from the University of Los Andes at Bogotá, Colombia. Currently, we're more than 80 students from more than 10 different careers committed towards developing robotic engineering projects. Having learned from our mistakes of past UFCs, we have developed and tested new Robocol subsystem that allows us to traverse difficult terrain, increases the handling per arm, and grants us a remote operating range of up to a kilometer.
To achieve a successful participation in this URC, we set both a system engineering and code design philosophy. As such, we read the requirements and met them with 7 technical subsystems and 2 general market subsystems.
The rover's chassis is made up from 2020 modular aluminum profiles which guarantee adaptability and structural integrity at all times. For the rover to traverse uneven terrain, we got inspiration on the Mars rover rocker buggy system, with the difference that ours only has 4 wheels. Furthermore, our rockers were made up from aluminum arch tubes for optimal force distribution. For transferring movement between rockers, the rover has an aluminum differential bar under its chassis, completely designed on AutoCAD software. It is also aided by a pulley system for improved stability. The wheels were designed with a honeycomb pattern, known for its exceptional strength-to-weight ratio. These wheels were simulated on ANSYS deformation analysis software.
In Robocol, we have a Jetson TX2 that works as the central axis of our entire electronic architecture, which has been designed and manufactured by the motion control team. Also, we have peripheral boards that are executing parallel tasks and communicating with our Jetson. These allow us to have a modulated and decentralized control of the rover's functionalities. The communication system allows us to connect with the rover from long distances through antennas with 13 dBA gain, rockets that operate at 2.4 GHz, and routers to which all of the devices are connected. We have developed path planning algorithms based on Dijkstra and SAR, control systems that use odometry given by an inter-real sense odometry camera, and manual remote operation codes, among others. All of our algorithms works inside a ROS melodic workspace, which is the framework that matches all of our subsystems.
To complete the task, we developed a 6 degree of freedom serial manipulator which can reach every position.
It is important to say that this robotic arm can be controlled with inverse kinematics during the equipment servicing, which allows us to implement linear trajectories that position the end effector close to the panel and then operated by direct kinematics.
The arm is composed of stepper motors whose drivers are controlled by NVIDIA Jetson, which runs the script that moves each motor independently. To improve cable management, we made use of the I2C protocol.
These aspects don't give us only precision, but also the necessary strength to complete the stream retrieval task. Hence, we're able to lift 5 kilograms and move the object to another position.
In the software team, we are in charge of developing algorithms for image recognition and remote teleoperation. For image analysis programs, we use Python with OpenCV, Aruco, TensorFlow, and NumPy libraries.
The user interface team developed a web application to allow easy access for monitoring and tracking the rover. The web app implements the Angular framework to provide a user-friendly tool and implements WebSockets in Django to exchange information between the web application and the ROS nodes.
In addition, we have 5 available cameras for the pilot, which allows odometric estimation and depth calculation. Finally, we fulfill the autonomous task detecting the AR tags and calculating the distance with our rover.
For the power subsystem, we use 6 lithium polymer batteries. Symmetric custom PCBs allow for modularity and flexibility. These enable 2 interruptions for each power outlet, an on-off switch and an emergency stop button. Furthermore, it permits for I2C communication with the Jetson in the main electrical box, and for an external power input that charges the batteries through a battery management system.
The science model of the rover is composed of 2 main subsystems, a sample collector and an analyzer denominated Ramses, and onboard lab denominated EVA. Ramses consists of a bucket wheel excavator that retrieves surface soil samples, sieves them to a specific grain size, measures their temperature and humidity, and transports them to the EVA. It is also equipped with a microscope. There are separate compartments for 4 distinct samples and 6 chemical tests to evaluate and conclude the existence of life.
Throughout this process, we have been supporting the development and progress of our team in the rover project. This work goes from the management and organization of the other subsystems to communication and relationship that allow us to get a sponsorship. In the end, big ideas need friends. That's why sharing and helping with the design process of sending our rover to Mars is a main objective.